Hello all, this is the second session of the chapter Stereochemistry, and in this session I'll explain Introduction to enantiomers, the relation between enantiomers and their specific rotations, and diastereomers. In the last session itself, we have seen one of the main conditions for a molecule to be optically active is they should have non-superimposable mirror images. Such compound who is having non-superimposable mirror images can be termed as enantiomers. So enantiomers are those compounds which are having non-superimposable mirror images. For example, one example can be given as lactic acid. The simple formula of lactic acid is shown here. This is 2-hydroxypropanoic acid, where the central carbon atom, whether it is chiral or achiral, this is a chiral carbon because this carbon atom is connected to 4 different groups. 1 to hydrogen, 1 to methyl group, 1 to hydroxyl group, and other one to carboxyl group. So this molecule possesses the condition to satisfy optical activity. So this is a chiral carbon, and whether it can be, now we should see whether it has non-superimposable mirror images or not. So the three-dimensional structure of this lactic acid, one structure can be represented like this, where the same structure, the three-dimensionally we have to represent like this, where the first structure and the second structure are the mirror images. This is a mirror image of the other one. So now we should see whether the first and second are non-superimposable or not. So how to see that? You just pick out the compound number 1 and keep over the second molecule. Just take the first molecule and keep it over the second molecule. Then how the molecule or the group will look like? On the second molecule, CH3 and carboxyl group will coincide, and carboxyl and CH3 will coincide. OH will be in one direction, and in this case OH will be on the other direction. So it is not superimposing. We can say it is not superimposing, or the structures 1 and 2 are non-superimposable mirror images. So we can say this is enantiomers. 1 and 2 are enantiomers of lactic acid. Now compound 1 and 2 are mirror images which have same physical and chemical properties, but in what property, in which property they'll differ? They will differ in the direction in which plane polarized light is rotated. So they differ only in the direction of rotation of plane polarized light. So such compound which are similar, which are having same physical and chemical property, but only they differ in the direction of rotation of plane polarized light, can be termed as enantiomers. An enantiomer is named by the direction in which it rotates the plane polarized light. Means if the enantiomer is rotating the plane polarized light towards clockwise in the right direction, we can call it as D form or dextro form, or we can label it as plus form. Or if it rotates it in the anti-clockwise direction, then we can label it as levo form or minus form or L form. Now, there is a term called external compensation of optical activity. What is that? So, to understand that, we should first understand what is racemic mixture. So, the DL, or the plus or minus racemic lactic acid, is an equimolar mixture of D and L lactic acid. Any enantiomer, not only lactic acid, any enantiomer, any optically active isomer which is having enantiomers will be having D form and L form. Now, an equimolar mixture of D and L form of the enantiomers will be termed as racemic mixture, or D and L equimolar mixture lactic acid can be termed as racemic lactic acid, which is represented by plus minus lactic acid, or DL lactic acid racemic mixture. The optical rotation of D and L are equal in magnitude but opposite in direction. Hence, optical rotation of one molecule is cancelled or compensated by the optical rotation of the other form. As a result, racemic mixture is optically inactive. So, the mixture as such will be optically inactive. D form will be optically active, L form will be optically active, but the racemic mixture which possesses equimolar mixture of D and L form, where both are having opposite direction of rotation of plane polarized light, that will be, the mixture will be optically inactive. So, this type of optical inactivity is termed as external compensation of optical activity. Now, what are the different ways by which we can represent enantiomers? There is a one formula given by Fischer, and we can term it as Fischer projection formula. So Fischer proposed an easy method for showing a spatial arrangement of groups around a tetrahedral carbon atom on a two-dimensional paper, because all these molecules are three-dimensional molecules. It is very difficult to represent three-dimensional molecule on a paper. So we need to represent that one in two-dimensional. So how can we convert the representation of a three-dimensional molecule into two-dimension? For that, Fischer has given an easy way where the asymmetric carbon lies in the plane of the paper and shown by intersection of the two crossed lines. Then vertical substituents represents the bonds going away from the observer. Then horizontal substituents represent the bonds going towards the observer. Then the important functional group is placed at the top. See here, this is one, the first one is a three-dimensional representation of the molecule. Now, how this can be represented in two dimension? Only thing is these two which are vertically written can be represented. We are keeping on the vertical line. These are the group which are away from the viewer. They are represented on the vertical line. And these are the group which are towards the viewer. They are represented on the horizontal line. So this three-dimensional structure is easily represented in two-dimensional on a paper in this form. This structure, this way of representation of the molecule is termed as Fischer projection formula. Now, coming to diastereomers, what do you mean by diastereomers? Or what is the importance of diastereomers? So to understand that, we should think whether all the optical isomers are enantiomers. Whether all these compounds are which are having non-superimposable mirror images are having, they will be enantiomers, but all optical isomers will be having non-superimposable mirror images. Stereoisomers which are non-superimposable, non-mirror images of each other, which have different physical and chemical property. They have different physical and chemical property. Whereas enantiomers, they are having same physical and chemical property, but they are having non-superimposable mirror images. They are termed as, these type of molecules are termed as diastereomers. They are also non-superimposable mirror images, but they differ in the physical and chemical properties. Now, for diastereomers, the particular isomers are erythro and threoforms. The two isomers are of diastereomerism are erythroform and threoform. Erythro and threo system of nomenclature is used for diastereomers having two asymmetric centers and has a structure of this kind. Here there is a molecule. Here there is a molecule. When we write this one, this here both chlorine atom, both are in the same side. So we can call it as erythroform. Here it is antiform, Cl and Cl opposite form. We can call it as threoform. When two like groups are on the same side of the molecule, the isomer is erythroisomer, and when they are on the opposite side, the isomer is said to be threoisomer. So from this session, you all will be able to answer, define enantiomers. What is the relation between specific rotation and enantiomers in like dextroform will be rotating towards the right side, then levoform will be rotating towards the left side in that way. And what do you mean by diastereomers? How diastereomers will be differ from enantiomers?